Lesson, we will discuss another method of solution in finding the general solution of a certain differential equation. So this time we have the linear equation of the first order. Then the idea is that we have to consider the general form of it. So we have that the differential equation of any order which is of the first degree in the dependent variable, and in each of its derivative is called a linear differential equation. So this is our linear differential equation of the first order. We have derivative of y with respect to x plus p of xy, and this is equal to q of x. For this, we have a solution that we have to multiply both sides by the e raised to integral of px dx, which is our integrating factor. So when we multiply both sides, that our general form of the linear equation of the first order, so it becomes by dy with respect to x multiplied by the integrating factor e raised to integral of px dx, and then plus p of xy e multiplying by the integrating factor again, e raised to integral of px dx, and equal to q of x times e raised to integral of px dx. So therefore, we can simplify this in the form of dy with respect to x, y times the e raised to integral of px dx, and this is equal to q of x e raised to integral of px dx. And by integration, this is now our general solution. This is y e raised to integral of px dx. And this is equal to the integral of q of x times the integral of, or the integrating factor of e raised to integral of px dx and dx plus c. And this is how to find the integrating factor. That for the integrating factor, it is necessary that we have to multiply by the integrating factor in our general form for the linear equation of the first order. So we have i's of x, if we will consider the i's of x as our integrating factor here. So multiply by derivative of y with respect to x plus integrating factor times p of xy is equal to derivative of i's of y with respect to dy. So this means that we have the i's of x times p of xy equal to the i's of prime, which is the derivative of x of y. And since the p of x is also I prime of x over I of x, so by integration, the I of x now is equal to the integral of px of dx, which gives us our integrating factor equal to e raised to integral p of x dx. So this is how to derive the integrating factor as e raised to integral of p of x dx. But for our solution in finding the general solution for a certain differential equation by means of setting into linear equation of first order. So this is how it is. For a certain given, it should be in general form or in standard form of linear equation of first order. So we have dy with respect to x plus y cotangent x is equal to 1. Now, in this example, it is already set into standard form of the linear equation of order 1. So this is our dy with respect to x, and then this is our piece of x, and this is our q's of x. So first step is we have to look for the integrating factor, which is the piece of x as our cotangent x, and the integrating factor is e raised to integral of piece of x dx. So if the piece of x dx is cotangent x dx, so we can find the integral of this. Integral of cotangent x dx is ln of sine x. And from our logarithmic rule, e raised to ln or e raised to ln is 1. So then, our integrating factor here is sine of x. Then all we have to do next is multiply both sides by the integrating factor. And this is our general solution. We have y e raised to integrating factor multiplied by integrating factor, and our integrating factor is sine x. And then for the q of x, we have sine x dx. So therefore, we have the integral of dy here. So this is y. So we have sine x y. And on the right side, we have the integral of sine x is negative cosine x. And then upon integration is plus c. So therefore, dividing both sides by sine x to find the solution y. So divide by sine x. So we have negative cosine x over sine x. And then plus c, the constant c over sine x. From our basic identity, cosine x over sine x is cotangent. So we can express this as negative cotangent x. And 1 over sine is cosecant. So we can also express the general solution as y equal to negative cotangent x plus c cosecant x. For our next example, we have dy with respect to x minus y equal to e raised to 2x. Again, in this example, it is already set into a standard form of differential equation of first order, where our piece of x here is negative 1 and our q of x is e raised to 2x. Therefore, we can find the integrating factor, which is e raised to integral of piece of x dx. And since the piece of x is negative 1, so this is simply negative dx. Then we can evaluate the dx as negative x. So our integrating factor is e raised to negative x. Since the general solution is we have to multiply by integrating factor, therefore we have the y here times the integrating factor e raised to negative x, and then on the right side, the q of x, which is e raised to 2x, and then times the integrating factor e raised to negative x dx. Then simplifying, this is now e to the x because e to the 2x times e raised to negative x is only e raised to x. Then we can evaluate the integral of e to the x dx as e to the x upon integration plus c. Then simplifying our equation, removing the e raised to negative x here, divide both sides by e raised to negative x to obtain the y. Then this is also means e to the x over e raised to negative x. Therefore, this is e to the 2x. And then, over e raised to negative x, expressing into numerator, so it becomes positive x. So, e raised to x. Therefore, our general solution is y equal to e raised to 2x plus c e raised to x for that example. For our next example, we have x dy over dx minus 2y equal to negative x. Now, in this example, it is not set into standard form. So, first thing to do is we have to divide by x. The equation should be divided by x to remove the x in the dy with respect to x here. So, dividing by x, it is now expressed as dy with respect to x minus 2y over x equal to negative 1 because negative x divided by x is negative 1. So this is now our piece of x, which is negative 2 over x. And this is our q's of x. Then we can find the integrating factor since our piece of x is negative 2 over x. Therefore, the integrating factor now is e raised to integral of px of dx, and since the piece of x is negative 2 over x, then it can be integrated by leading to ln here. So dx over x is ln of x. So we have e raised to negative 2 ln of x. And then by rule of logarithmic, we can express the negative 2 as exponent. So it is now e ln of x raised to negative 2. And e raised to ln is 1. So therefore, the integrating factor is x raised to negative 2. The next step is we have to multiply the integrating factor as for our general solution. So from the given differential equation, multiplying the integrating factor as x raised to negative 2 So this is y raised to negative 2. Integral of dy is y. And this is now multiplied by x raised to negative 2. And for our q's of x now, this is x raised to negative 2 dx. And then upon integration plus c, so we have here as y x raised to negative 2, and then this is by means of power, negative 1 over negative 1, so we can have x raised to negative 1 here, and then upon integration plus c. So simplifying, solving for the y, divide by x raised to negative 2. Therefore, we have as y equal to x and plus cx squared. And that will be our general solution for that example.